today we're going to talk about eigenvalues and eigenvectors and how to find them. I mean, if you translate that, A is my transformation, okay? And then I have my vector, which is going to be my eigenvector. And when it says it right here, an eigenvector of a transformation is a non-zero vector that changes at most by a scalar factor when you apply it. So that's saying the vector doesn't change at all. It does change a little bit. It changes by a scalar. The scalar that we will use here on the right side is called lambda, okay? That lambda is going to actually be my eigenvalue. So lambda is my eigenvalue. And V is going to be my eigenvector that we're talking about in that sentence, okay? Now, how are we going to find it? So how about let's play around with this AV minus lambda V, equals, right? So what we're going to do, there's always a lot of telling stuff when we have 0 on one side. A lot of, when we solve, we set it equal to 0. So I set that equal to 0. And if I factor out V, I'm going to factor it out. I have A minus lambda. Lambda is a constant, so I do need to multiply it by... because we can only subtract if they're the same size. So I will be, if this is A is 2 by 2, I is my 2 by 2 identity matrix. Okay? So do note, though, just looking at this, so my note, because this is the original one we start with, we can clearly see V equals 0 it's called a trivial solution. Okay, but it is a solution. So we have an automatic V equals 0 being a solution. 8 minus lambda I times V equals 0 has more than one solution if and only if the determinant of A minus lambda I equals 0. Okay? And when I talk about more than one solution, if we can set that equal to 0, then we have a second solution, the first solution being my trivial solution, okay? Eigenvalue. So, again, we're going to use this here to find it, to find our, that's going to be our characteristic equation too, in order to find our eigenvalues. So we're going to find the determinant of A minus lambda I. First we need to find A minus lambda I. Let's write it out. It's 3. We won't always write it out this long, but this is my A, 3. Okay. So this is A minus lambda I. So let's do that. And now I could subtract term by term. It's 3 minus lambda. 2 minus 0 is 2. Minus 1 minus 0 is minus 1. And 0 minus lambda is that. Okay, so that's my A minus lambda I. And let's find the determinant of that. Going to be equal to, going to be minus lambda, 3 minus lambda, minus a minus is a plus 2. My characteristic equation is basically I set my determinant equal to 0. Now to find the corresponding eigenvectors. So for lambda, we have to do lambda 1 first, column 1 to corresponding. So lambda 1 is 1. So here, up here is my a minus lambda I. So I'm plugging in lambda equals 1 into there. So to find that, it's basically 3 minus 1, because that's my lambda. 2 is there, minus 1 there, and then minus 1. Okay? Because my lambda was 1. So that's equal to 2, 2, minus 1, minus 1. So remember, what we want is a minus lambda I x is equal to 0. That's what we want to solve, right? So we times it by x is equaling to 0. We can do our 2 by 2. And if we even want, we can do xy, because that's our unknown. It's going to be a column vector. Okay, so that's what we have here. And now we need to solve it. This is my v. That's my v. We can see here that this a, 2, 2, 2, 2, minus 1, minus 1, it does reduce to 2, 2, 0, 0, okay? Let me show you how to do it. Basically, you could take any of those equations. So what we're looking at here, and let's take our first one, 2x plus 2y is equal to 0, right? That's from doing this and equals to that. So that's one of our equations. Our second one doesn't give us much because it's going to be the same equation, really. That's how that reduces down to 0, 0. Yeah, I got 0, 0 there in case you're wondering, because I can see they're the same, they're just multiples of each other, right? 2, 2, and minus 1, 1. I can row reduce it by taking a half of row 1, and I'm adding it to row 2, and I'm changing that into row 2. Okay, that's how I can look at it. If they're multiple rows, it's going to go to 0. Okay, so this first equation that I get, 2x plus 2y, and I could have reduced it to 1, 1 if I wanted to. It doesn't matter. 2x is equal to minus 2y, because that will divide out. We get x is equal to minus y. I'm solving xy, okay? How can xy be represented? Well, we see here that x is a combination. It's just negative y. So I can replace y with negative x, or vice versa, okay? Doesn't matter which one you substitute. Clearly y is negative x. I could have done y too. So I can say, hey, well that's, I could pull the x outside, and then I have 1 minus 1, okay? So this is these are all equal. And so this right here is my eigenvector. That's my eigenvector. See that x? X could be anything. X is any number, okay? So we could have, called it t. Okay, so t times 1 and negative 1, or just any number. Okay, times, it's kind of like your c when you're solving differential equations. Like there's your bases, and you times it by c, t, x, anything you want to call it. So that's what we're looking at. This is going to be part of our bases, and that's my first eigenvector that corresponds to my, that's going to span, my span of 1 minus 1 is my eigenvector for lambda is equal to, what was that lambda? 1. Okay, so let's do this again for a second. That was for lambda's 1. Now we have to do it for lambda is equal to 2. So lambda equals 2. Lambda equals 2. We have, again, we're just doing, just want to see it. So this one up here, it's 3 minus 2, 2 minus 1 minus 2, right? 3 minus 2, 2 minus 1 minus 2. And that reduces to 1, 2, minus 1 minus 2. That can reduce to 1, 2, 0, 0. The way I actually like doing it personally is see how you have, and this is x, y equals 0, 0. So what I think about is instead of using x like I did up here, I like to use a parameter, a constant, right? I can see here my second row here is my y value, my y. It's going to be that times that equals that. It's your positional. So what I'm going to do is I'm going to set y is equal to t, a parameter. Okay, you don't have to do the 2 by 2 this way because you'll be able to figure out your eigenvector without doing this. But when I get to the 3 by 3s, it really helps me keep track of all the 3 of them that are going on. So if I set y equal to t, then I have my top equation is 1x plus 2y is equal to 0. We get that one. And so I have something to plug in for y now, right? So now I want, basically you want x in terms of t and y in terms of t, if you can. So x plus 2t equals 0. And so now solve for x in terms of t, it's minus 2t. And that's good because now I have my x, y is t, and x is minus 2t. You know, you can start from the top too. You can call x equals t and then go downwards. But I don't know, I like doing it this way. So now I can see my t minus 2, 1. And that's it. Okay, so there's another theorem. Theorem says the eigenvectors, the claim is that 1 minus 1 minus 2, 1 are, that these are independent. So how can we check independent? We can use the Wronskian by taking the determinant, similar to what we did with the Wronskian. And we get 1 minus 2 negatives positive, it's negative 1, which doesn't equal to 0. So therefore 1, 1, and minus 2, 1 are linearly independent. So we gotta find a minus lambda I, which is gonna be 1 minus lambda. You're basically just subtracting out lambda from the diagonals. Remember, we're going to choose the column with the most zeros, so that's my winner. So it's going to be 1 minus lambda times inside there 2 minus lambda. We have 2 of them, minus 1. So my characteristic equation, it's going to be 1 minus lambda 4 minus 4 lambda plus lambda squared. Okay, so we have for lambda 1 is equal to 1. We're going to plug it into that equation that we just got. So we plug 1 in to all these lambdas, here, here, and here, to get a new matrix to find the eigenvectors. So 1 minus 1 is 0, 0, 0. 6, 2 minus 1 is 1, 1, 0, 1, 1. Okay, so for this one, x could be anything. So my first line right off the bat, though, I have 6, well, this is times x, y, z equals 0, 0, 0. So you don't, sometimes people don't like to write that, but I do. Because that's what we're solving. We're solving for x, y, z. So my second, just my first equation, I'm seeing I can solve 6y equals 0. Do you see that? I've got this times this, and only the 6 and the y are standing. So y is equal to 0. So x is 2, y equals 0. And we need one last one. So we can use, they're both the same equation. Y plus z equals 0. Let me show you where I got that. Doesn't matter first or second. Here and here. Sorry, here and here. We can see it now, hopefully. This times this is x. This times this when I'm dot producting them. And so y is 0, right? So 0 plus z equals 0. So z is 0. So what do we have? X, Y, Z. X, Y, Z is equal to t 0, 0, which is equal to t1, 0, 0. You see that? How that works? 0, 0. So that's my eigenvector. My first eigenvector for 1. So now lambda 2 is equal to 3. We plug it in again here. 1 minus 3, 2 minus 3, 2 minus 2. 2 minus 3 is minus 1, minus 1. Everything else is the same. Okay? Oh. And I don't want the straight line. I just went straight accidentally because I held it. Okay, so now, see how these bottom two rows, if I add them, I get 0. When I add the bottom two, I get 0. Row of zeros. So that's in my z position. So that's why I set z is 0 equals 0. That's what we have, right? When I set that equal into 0. If you want me to write it out, I can. I have times my x is equal to 0. Okay, so z is equal to 0 equals 0 in my z position. So it's t, meaning my last row. 0 equals 0. Okay, so z equals t is my parameter. And then let's try to get the other variables in terms of t also. So my second line is minus y plus z is equal to 0. So minus y plus t is equal, z is t, 0. So y is equal to t. I can see that. And now x. So I go to my first line now. Now I'm going here. And it's minus 2x plus 6y equals 0. And it's minus 2x plus 6t equals 0. And then 2x is equal to 6t divided by 2 divided by 2. X is equal to 3t. Okay. So we got them, circled them. So x, y, z is equal to x is 3t, y is t, z is t. It's equal to 3, not 3, I'm pulling the t out, sorry. T, 3, 1, 1. There's my second eigenvector. There's 1. There's 2. And one more. Oh, no, that's it, because we only had 2. So my set of eigenvectors is 1, 0, 0, comma, 3, 1, 1. Okay, next example. So I guess this is going to be the winner. Plus, minus, plus, plus, minus, plus. Yep, so it's plus. It's equal to 5 minus lambda times 3 minus lambda quantity squared minus 2 is minus 4. And I get 5 minus lambda 9 minus 6 lambda plus lambda squared minus 4 equals 0. There's my characteristic equation. Lambda squared minus 6y plus 5 equals 0. And so I actually get 1 and 5. Okay, and so for lambda 1 equals 1, we got to plug it back into there, that equation up there. So it's 3 minus, we plug it in, lambda in here. So it's 3 minus 1 is 2, minus 2, 0, minus 2, 2, 0, and 5 minus 1 is 4, 0, 0. 2 minus 2, 0. See how these rows, we just add these together and add it to row 2. I get 0, 0, 0, and then 0, 0, 4. And if you want to see it with your setup, x, y, z is equal to 0, 0, 0. So we have the last line, 4z equals 0, so z is equal to 0. We see that, right? So my second line, there's nothing to grab from it, so there is what I'm going to call y equals t. There's my parameter. And then my first line is going to be 2x minus 2y equals 0. And so 2x minus 2t equals 0. 2x equals 2t, x is equal to t. Okay, I've got all three of them. So my bases is t, x, y, z is going to be t, t, 0. Which is t1, 1, 0. So there's my eigenvector. So let's do it again. For my second eigenvalue, which is 5. Gotta go way up here, so I'll be going 3 minus 5 is minus 2. Minus 2 in the middle, and 5 minus lambda, 5 minus 5 will be 0 there. Nice. So if we can remember that, just so far up there. It's minus 2, the rest is the same, minus 2, 0, so I could look. Do we see that we also have another row of zeros? Look at that. Those rows are identical so that you can subtract it out. 0, 0, 0, 0, 0, 0. And so we are going to call z my first parameter, and we have y can be anything also. That's going to be my second parameter. If you have two parameters, you got to give it a different letter. So I'll use s, or you can use t1, t2, it doesn't matter. So y is s, and then we can just copy the first line, minus 2x minus 2y, and set that equal to 0 using my equation. And plug in your parameter. We want to solve for x. 2s is equal to 0. So solve for x, and we get minus 2x is equal to 2s. 2's cancel, and we get x equals minus s. Okay, so let's circle those three. Okay, so we've got all of them in terms of our parameters. So x, y, z is equal to x is negative s, y is s, z is t. Okay? But that's two different constants. So just like before when we separated, we had three different independent variables. We had to have three matrices. Not matrices, yeah, vector matrices. So we're going to write this is minus s, s, 0. Separate the s's and t's, basically. Plus 0, 0, t. Which this is equal to, pull the s out, minus 1, 1, 0. Here I'll pull the t out, 0, 0, 1. And therefore, guess what? We got two eigenvectors. From the one eigenvalue. Okay? So how do I write that? We can span minus 1, 1, 0 and 0, 0, 1 spans eigenvector for 5. And just a note here, putting all three of them together, we have three eigenvectors, right? Those are my second two, 0, 0, 1, minus 1, 1, 0. My first one, I gotta go back and look. 1, 1, 0. 1, 1, 0. Let's find the determinant of this to see if they're independent. We're not guaranteed for these to be independent because we didn't have three distinct eigenvalues. So we don't have any guarantee it is, so let's find out. I'm going to use this bottom one, and it's going to be 1 times 1 plus 1. 1 equals, just 2. 1, it's 2, which is not equal to 0, so yes, therefore they are all linearly independent. Okay? The algebraic multiplicity, and I'm not going to write that out every time, it's AM. Okay, think of like AM, PM, it's algebraic multiplicity. And what that is, it's the power, so you know what multiplicity is, it's usually the power of your eigenvalue, lambda minus lambda I. So if you have two of them, the multiplicity is 2. It makes sense in the characteristic equation. Okay? And that's one type of multiplicity. There's another thing called a geometric multiplicity. And that is GM. And that's basically your dimension of the eigenspace. Okay, and really it's how many vectors, eigenvectors, there are. For lambda 2 is equal to 5, the AM, the multiplicity, the power for 5, we had 2 factors that were 5, so the AM is 2. And the GM we ended up with was also 2. There was a previous example that we did. That was the very first example of a 3 by 3. Where here's my first example. We had a 3 by 3. We only got 2 eigenvalues. And from each of them, we only got 1 vector. Okay? So for this one, the AM for, which one was double? For 1. So the AM for lambda equals 1, we got 2, but the GM is, since we got 1 vector, it's 1. Okay? So they don't have to be equal all the time. Sometimes they are, but sometimes they're not. But the rule of thumb is that, in general, the GM is less than or equal to the AM. Okay, that's it.